like this. Okay. So we're still working on the theory. So here's some preliminary results. So motivation. Imagine we have some basic, very simple data, consumption data from where we have demand and supply data information. Now, how do we estimate the demand curve? That's the question. Suppose, all right, because this data is a fake data. It's generated from a model we know. So suppose the data is generated by utility maximizing consumers subject to budget constraint, and where the utility has a CS form, we have the good and outside good, and with a given the RCT distribution. So suppose this is the model that generates the data. Now, but we don't know the model, right? So we only see the data. So how do we estimate the demand curve? Well, we could just fit a statistical model. And what kind of statistical model do we fit? Can fit anything. We can use any parametric and parametric model that fits the data well, right? We can do that. So here I'm just fitting a second degree polynomial to the data, assuming the price is exogenous. I'm not going to worry about endogeneity here. So suppose the price is exogenous, I can just fit a statistical model. It's pretty easy. Okay, now, however, we can choose any model to fit the data very well. However, if we ever want to extrapolate beyond the observed range of the data, so for example, if I'm interested in what's the demand going to be like if I double my price, then the statistical model will extrapolate very badly. So here the green one is the true model, and the red one is the statistical reduced form model, which is very badly extrapolated. So that's because, as we all know, that a major assumption for any standard statistical or machine learning models is that the training data and test data must be drawn from the same distribution or domain. The task of extrapolating into unknown or extrapolating to further data is the task of transfer learning, where we are essentially trying to apply a model that's estimated on the source domain to a different target domain. And if we don't have test data in the target domain, then the extrapolation would be pretty bad, or there's no guarantee for its performance. Right. So in contrast to this statistical approach, we could estimate a structural model that we believe describe the mechanism that generates the observed data. So so essentially we could go back to estimate, this type of model, right? For example, suppose we know the correct form of the utility function, we just don't know the parameter, and we can estimate the utility function, we can estimate the parameter, and then use it to generate our estimated demand curve. So this approach, as everybody here is familiar, is the structural approach that essentially we're estimating causal models based on economic theory, which we believe describe our observed data well. So more generally, any models that use economic theory to specify the functional form of causal relationships can be described this way, right? Okay, so because structural models are based on economic theory, we think that the parameters are deep. In other words, in the language of transfer learning, parameters we believe are domain invariant. So a structural model, in this sense, estimated from a source domain, can be applied to a different target domain, which gives the model generalizability and external validity. I would argue essentially that's what counterfactual analysis is, right? So structural model has been always used to do counterfactual analysis, which is a special form of out-of-domain prediction problems. However, as we all know, validity of structural approach hinges on the model being correctly specified. In practice, we have all these sorts of assumptions and may not be, assumptions, especially of functional form, that may not be correct. So that brings us to the competing paradigms, where there's a disagreement over the role of theory in learning. So I quote two titles of two papers. One is by Warping. This is The Limits of Inference Without Theory, the other by John Rost, The Limits of Inference with Theory. So this is a quote from John's paper, which says, notice the huge difference in worldviews. The primary concern of Beamer, Mansky, etc., is that we rely too much on assumptions that could be wrong. and which could result in incorrect empirical conclusions. While on the other hand, Wolping argues that assumptions and models could be right, or at least they provide reasonable first approximation to reality. And hence, we have two worldviews of how to approach empirical problems. So the question we ask more generally here is that, is there any way to combine the two approaches, statistical and structural, to achieve more external validity than simple reducible statistical models, while being more robust against misspecification than structural models? Okay. And our idea is extremely, the idea is extremely simple. We're still working on the theory is much harder. I think extremely simple, which is we're just going to treat a given structural model as not as the truth. We don't estimate the structural model and stop there. We estimate structural model, we treat it as a benchmark model, and we estimate a flexible statistical model with a penalty on deviance from the structural benchmark. That's why it's a regularization approach, and so we're using the structural model as the regularizer for our statistical model. So that's why we call it a structural regularization estimator. The intuition here is that we want to use theory not as a truth, but as a guide or as a prior knowledge. Well, so this is so as a preview of very simple the very simple example we gave at the beginning. If we so this is the true model, and this is the statistical model which extrapolated very badly, and the brown curve or the red curve is the result of using structural model as a regularizer, we call SRE, and you can see that. So in this case, the true structural, like the structural model is the true model. So obviously it's the truth, it's the best fit, right? But using it as a regularizer, which we call SRE, also performs pretty well, or we extrapolate beyond the given domain. Now, on the other hand, our structural model can be misspecified. So suppose we go back to estimate the CS functional form, but well, actually, suppose we don't estimate it. We just assume it's a CS utility function, but with elasticity of substitution being 0.5 rather than negative 0.5. If we do that, then the structural model would be systematically wrong. It's not a true model anymore. So the true model here is the red one. The structural model is the green one. It will give you a misspecified structural model, which does not perform very well. However, the SRE can still fit both in domain and out domain pretty reliably in this case. So this is the result we want to show intuitively how this thing works. Yes. Yes. Well, here we just want to illustrate the fact that if our structural model is incorrect, so regardless of how it is incorrect, right? We could estimate a wrong functional form and arrive at an incorrect result, or we could just assume an incorrect structural model, and we just show that in this case it's the result we get. Okay. So the literature we speak to, well, there's a whole literature in transfer learning with covariance shift, which doesn't really apply here because in machine learning, when people do transfer learning, a large literature typically assumes that in the target, so either we have test data in the target domain, or we assume that in the target domain, the conditional the conditional probability of y given x is the same as in the source domain, and that's how people perform transfer learning, which is not the case here. Okay, so here we don't assume that the conditional probability of y given x is always the same. So that allows us to address a problem that is typically not addressed using available transfer learning methods. We also speak to the literature on combining statistical structural estimation and as well as robust structural estimation against model misspecification. There's also recent literature examining the transfer performance of economic theory. So the paper by Isaiah Andrews et al., also Fudenberg, I think, so the 2022 paper, basically estimates a structural model of behavioral CPT, cumulative prospect theory. They estimate it using both structural model or using machine learning, and they examine what is the performance of this model across all kinds of different domains. And their conclusion is that structural model is not as good as a statistical model in domain, but can outperform statistical models out of domain. So the reason why I specifically mention this paper is that we use their data set as well to examine the performance of our approach. And finally, there's a paper by Fessler and Max Casey in Restat that have the same intuition. They are saying we use theory as a regularizer. Now, however, in their approach, the theory is basically our binding constraints, such as alpha1 equal to alpha2, and then we have some prior on that, and they only examine in-domain performance rather than out-of-domain performance. But to us, the in-domain performance increase of any regularization approach is not really due to theory. Right? It's more due to in-domain you can overfit with an arbitrarily complex statistical model. So anytime regularization, it shrinks toward a more stable, not overfit functional form, so which helps performance. But at least my understanding is the only, like in domain, there's no competitive advantage of any structural models. So the only benefit of having, at least to me, my understanding is the only benefit of doing structural is that we want to do out of domain prediction. So in order to justify that, right, we need a theory that says that combining structural with reduced form can increase out of domain than in domain. And then the theory part is very difficult. We're still on it, but there we go. Now, our approach has several sort of small methodological features that we need to work out in order to make this work. But the overall idea is very simple as presented. So basically, our setup is we have we suppose we observe variable x and y that belong to a joint distribution, and we're interested in a large domain, but we only observe data in part of the subdomain. So the statistical or ML machine learning algorithm built on random sampling assumption will not be able to learn the true functional form of on the whole domain, but only a subdomain that we observe. And let the model M, being a structural model that describes the causal mechanism based on our knowledge. It could be true, it could be misspecified to some degree. So in order to do this regularization approach, we tried several different algorithms. The one that performs best is the one I'm presenting here. So basically what we're going to do is going to ask the structural model on the data we actually observe. And then we are going to use the estimated model to generate synthetic data. The structural model is a generated model. Once we estimate the parameter, we can use it to generate the data in any domain. Right? So we're going to use the estimated structural model to generate synthetic data in the entire domain including the target domain we're interested in. And then we're going to derive any relationship between y and x, the reduced form relationship that we're interested in, based on the generated synthetic data. So which what we call FM. So FM is the generated statistical relationship between y and x based on the estimated structural model. So in this sense, structural models are because in the statistics, there's also a whole debate about whether we should use generated models, discrete models. So here we're essentially using structural model as a generated model from which to derive discriminative relationships. Okay, so then we go to the second stage. So the second stage is estimating the regularization approach, where we're essentially estimating any kind of flexible statistical model with the theta m with a penalty on deviance from the structurally derived theta parameter. Okay. So what is the structurally derived parameter? Well, the structurally derived parameter is a flexible statistical fit to the generated synthetic data, or to the f function that we can derive. Okay, so basically we use the estimated structural model to generate a bunch of synthetic data, and then we fit a flexible statistical functional form to it and derive theta m. So theta m represents the structural or theoretical value of theta, and then we go back and estimate and fit the flexible model to the original data with a penalty of deviance from the theoretically derived theta m. So that's sort of the picture we are doing here. It's again very simple approach. The interpretation again is that we can think about this as essentially using theory as a prior knowledge. And I would argue that it makes a lot of sense because theoretical model itself is indeed formulated based on the whole history of observed data that we previously have in economics, and based on which we formulate over this theory. So that theory should be viewed as a prior knowledge and very reasonably. Yes. Right. Yes. Yeah. Well, right. Right. Yes. Well, thank you very much. That's a great question. So indirect inference is a way of estimating the structure model. So you're still assuming the structure. Functional form is constrained, but so here we're basically saying that the functional form could be misspecified. So we allow deviance from the whole class of model, like from the whole set of models within the structural class, within the structural function. So if using the very simple example here, I can estimate this little structural toy model without knowing the rho, and then or alpha, and I can use indirect inference, but it's not going to jump out of the CS form. Right? But what if the CS form itself is incorrect? That's right. So that's where I believe that. So our approach basically does not impose any functional form assumptions. Right. Yes. Okay. Right. So we non-parametric estimate with a penalty on D. Right. Okay. Right. Right. So our final estimator SRE, the theta is empirically driven. It's non-parametric fit to the data with the theoretical value as a prior knowledge. So we put a penalty on deviance from that. So we try to stick to the theory, but allowing deviance so that it can fit the data better. So it allows the better domain. Hopefully, it can extrapolate to the out of domain. Right. In practice, because these two-stage procedure, and especially if we're fitting a really complicated structural model in the first stage, then in practice we need to do sample splitting and cross-fitting in order to guarantee performance. So that's a very basic outline of the algorithm. We can also apply to causal analysis because the setup or the method can be very readily generated to method moments. So I will show. So we have an example showing how to do IV and how to do causal analysis. Please. Yes. Right.
It'd be interesting to extend this to, suppose you had a little data out there or something, and then how would you use the structural model to get there? I mean, the fact that it's not identified out there, that's, people don't think we should do that kind of extrapolation at all, right? So it's, the classic example is bunching, right? In the economics literature. So I think it's interesting. It's a very interesting framework, but it'd be interesting to extend it beyond the case where you don't have any identification at all.
I see. That's great. Thank you. Thank you so much for the suggestion. Yes, that's great. Okay. So so I'm just going to how many time? 10 minutes. Okay. So I'm just going to show you. So I'm going to show you some simulation evidence of efficacy, and then talk a little bit about where our theoretical sort of effort currently lies. So this is just some showcasing simulation showcasing how the method works. So the first example we do is a first price auction. So basically we generate n bidders in a sealed price in a sealed first price auction, We want to, right? So we suppose we're interested in a really simple relationship, which is the number of bidders and the winning bid. Now, of course, so the experimental setup is that suppose the true mechanism. We have 3 experiments. The first experiment, suppose the true mechanism is that the value is uniformly distributed and everybody's rational. So we're going to estimate a structural model based on Wong Kwong, Garrett, and Wong Kwong classic paper, and we're going to do basically estimate the structural model, assuming that people are rational and estimate it's uniform. And the second experiment is that we assume people are not uniform, beta distributed, and people are rational, so that our structural model will be misspecified. The third is that people do not people do not bid rationally, so that there's a random non-rational component, people's bidding behavior. The result, so the first experiment is that our structural model is correct, and in that case, everything is good in domain. So which means we're using only this data to estimate all the models, but then we want to extrapolate. Once we extrapolate, the statistical model, we're going to be very bad. The structural model is the true model, which is good. So is our SRE. In the second experiment, the structural model itself is misspecified. In domain, it is not good. Is not as good as the statistical model. So in domain, the statistical model and SRE perform better. Out of domain, again, the statistical model does not well. SRE is going to performance. The structural model is good in terms of extrapolating the trend, but it's way off in terms of the level. The third experiment very similar. Here we have people bidding irrationally, and to some extent where our method is able to correct for this irrationality that deviates from the rational benchmark. No, it means data from a probability distribution that is different from the probability distribution governing the source domain, governing the data where we estimate the model. So it's different from like test data that are drawn from the same distribution. Yeah. Yes, because as you can see, the true functional form governing y and x is different from once you go outside. So they are different from different domains. Oh yes, that's right. Yes, yeah. Yeah. Yes. Yes. That's a great question. I think personally, I'm not as confident in whether in the fact that I'm not confident with the statement that most of the structural model with zero improvement are actually pretty close. I'm I'm not as confident in that, but I guess this is so maybe you can think of my example as a slightly pessimistic view of the structural approach. Right. But anyway, so so I think both the example and the beginning example. The other thing I want to say about this is that the reason why we believe that in domain structural model does not have any advantage is because in domain we are essentially non-parametrically identify the functional form. But the reason why structural model can help is that it contains knowledge, right? That statistical models do not have. So for example, here there's a knowledge, economic knowledge, that the more people bid, right, the more we're going to eventually, get the draw from the rightmost of the value distribution. And this knowledge, if we don't use this knowledge, then we're not going to be able to extrapolate. Similarly, in the beginning example, there is knowledge economists have, which is demand curve is downward. We have to use that knowledge, fitting demand curve. We don't use that, then we can fit the model really well in domain, but we'll never be able to extrapolate out of domain. So this is really an effort to how to incorporate knowledge into our fitting. The second example is the dynamic entry exit. It's also extremely toy model. It's very, very simple. We basically have firms enter exit subject to entry cost, and then we assume that there's an exogenous market return to operating in the market each period. And I here I just assume a very simple target. Like suppose we're just interested in predicting how many firms will operate in the market based on the market return each period. So in this case, we can estimate a time series model, or we can do a dynamic structural model, DDC model, a la Miller, and we will be to estimate this whole thing. The setup we have here is that our structural model always assume rational. So here I'm doing some experiments on expectation. So a structural model always assume rational expectation, but the true mechanism can be rational, can be adaptive, can be myopic. Adaptive means people assume that yesterday will be tomorrow. Myopic is that people are not forward-looking. So these are the truth. The drawback of our approach is that we really need a very long time series. So this is unrealistic in most empirical calculations. But here we're assuming that we observe like 500 periods, and then we use the first half to estimate, second half to test our extrapolation performance. So basically the pattern is very similar to before. In experiment one, the statistical model does not, the structural model is the true model. So it can extrapolate really well, but the statistical model does not extrapolate very well. In the second experiment, the statistical model also pretty bad, but the structural model now is incorrect because we assume, because the true expectation is adaptive, not rational. But the structural model is still rational, right? So here, I believe, right. So this green line is the structural model, which is misspecified, and our SRE that is still pretty closely to the truth. And then finally, the third one is myopic, which is more or less the similar story. And then we have the multiple Monte Carlo run evidence that the SRE is effective in this case. Right. Yes. Right. That's right. I think that's the same critique. Right. I'm being more pessimistic, but I thank you so much for the comment. I think maybe we should try better structural model in this case, right? But on the other hand, you can say that a lot of people, when they actually do transformation, like you said, they try different functional form to fit the data. They add things and minus things, and that is also a form of data smoothing. It's very hard to put in sample data, which will lead to theory performance out of domain by itself, even within domain, but out of sample. So anyway, I think we can try more optimistic or better structural model here. Okay, sorry, yeah. So I skipped the amount estimation, but this is like using IV and using method moments. But let me just briefly talk about, and also we did an empirical application using the Andrews paper, Isaiah Andrews paper. Okay, so right, okay, so Our theoretical, we're still working on the theory part right now, but I think what we're trying to say here is that our setup assuming, okay, we're assuming that essentially we have two theta, one theta is theta A, which is governing in domain, the other theta B, which is governing the true theta in out of domain. And if we and the ideal, which is infeasible, but the ideal estimator is one such that given in a certain ball of misspecification, a certain range of misspecification, the optimal infeasible estimator is one that uses the non-parametrically identified theta A in domain, but then strictly uses the structural model out of domain, assuming that the structural model can carry some degree of extrapolation ability or out of domain prediction ability, right? Subject to misspecification, a range of misspecification. So we show that this kind of estimator is the minimax estimator that is optimal for our purpose, but it's also infeasible. So what we're trying to do is we're trying to show that the way that we are doing it, so which is our SRE, will essentially converge to this infeasible minimax operator estimator as sample size goes large. So we're still working on it. The idea we're trying to we're also experimenting improving our estimating in the sense that we believe the way that our estimator currently works is that but it's not optimal, because when we work on the theory, we realize that it's actually better to have two regulators. So one regularizer is for statistical stability, avoid overfitting in domain, and the other is for extrapolating out of domain. And that's what we realize when we work on the theory. So that basically also unifies our paper with the nice Casey paper, which is strictly about in domain. Because we want to say that if you regularize using anything, zero or theory in domain, it provides statistical stability. But then out of domain, it's really where the theory is useful. So we're still working on a convergence result, but that's
Okay, thanks very much for having me here. I'm a PhD student from UCL, and this is my dual market paper. It's about the robust dynamic structure estimation. The motivation of this paper is, in dynamic models, we always have potentially serially correlated latent variables like unobserved product characteristics in demand estimation, labor supply shocks in labor economics, and of course, we always have the utility shocks to the discrete choice. And as researchers, we do structural estimation because we want to simulate counterfactuals. And to simulate the counterfactuals, we have to impose assumptions about the dynamic process of those latent variables, so that we can solve the Bellman equation, we can compute the continuation value, and finally, we can simulate the counterfactual. And the misspecification of the dynamic process will lead to biased estimates of the continuation value, which biases the estimation, and which finally biases those counterfactual parameters. For example, price elasticities in demand estimation, or maybe consumer surplus from the electric vehicle subsidy. So in practice, what we have done to examine sensitivity is we have a reference dynamic process, let's say AR1 process, and we try alternative parametric processes, maybe serially independent normal distribution, and to see how those counterfactual parameters change. But the choice of the alternative processes is ad hoc and it's also arbitrary. So in this paper, what we do is we provide a framework so that we can perturb the reference dynamic process in a flexible and non-parametric way. And we want to see how this change the counterfactual parameters. And of course, this is a very interesting topic because it provides researchers with a systematic framework to do the sensitivity analysis. So this paper is about, we have a latent variable. It is potentially serially correlated. We worry about the misspecification of its dynamic process, and we want to do sensitivity analysis. And this paper is about how to do the sensitivity analysis. But it also brings a significant challenge. The main challenge here is we have a reference dynamic process and it is stationary. So it is characterized by the conditional distribution of the future latent variable given the current latent variable. It is stationary in the sense that this conditional distribution has the stationary distribution. And we will perturb this reference conditional distribution in a flexible and non-parametric way. And this perturbed non-parametric conditional distribution must also be stationary. And this stationarity condition is computationally difficult to handle. And this paper is the first one to provide a tractable framework, computationally tractable framework to deal with this stationarity condition. And to illustrate the framework, we have two empirical applications. The first is infinite horizon dynamic demand model, and the second is a finite horizon dynamic labor supply model. So the framework works for both finite horizon and infinite horizon. And in this talk, we will focus on the time homogeneous case, which means that the conditional distribution of the future latent variable, given the current latent variable, is time invariant. And in the paper, we also have a similar framework for the time inhomogeneous case. But in this talk, we will focus on the time homogeneous case. So to fix ideas, let's consider a very simple optimal stopping problem. This optimal stopping problem can be used, for example, demand estimation. At each period, a consumer decides to buy a car, then exit the market. So this is a stopping decision, or he can wait for the next period. It can also be used maybe in labor supply. So at each hour of the day, a taxi driver decides whether to continue working, wait for the next period, or stop working and go home. And in this problem, so we have two kinds of unobserved variables. The first is the KC. It can be the unobserved product characteristics in demand estimation or the labor supply shock in labor economics. And the second unobserved variable is the utility shocks. So in this example, we are not relaxing the extreme value type 1 assumptions. We are considering assumptions about the dynamic process of this KC. This extreme value type 1 distributions have to solve a smooth Bellman equation so that we estimate the welfare, which is the value function V. And here we have two conditional value functions. The first is the V1, because stopping decision is a term interaction, so there is no future. So that this V1 is fine, it's just a KC. But if we wait for the next period, we have to compute the value of waiting, which depends on the conditional distribution of the future, the T prime, given the current. And beta here is a discount factor. And if this conditional distribution is misspecified, it will lead to the bias estimate of this value of waiting, which biases everything. Even in this simple example, we can see that because this is a nonlinear problem and we have a dynamic problem, so the sign and the magnitude of the potential misspecification bias is unclear. And in this paper, we will provide a computational tractable framework to quantify the sensitivity of maybe the welfare to the assumptions about the dynamic process of this latent variable. So this is a simple illustrating example of the stopping problem. And we also have many other examples, for example, in industrial organization, in labor, in health, in trade. And of course, we always have the utility shocks. So my framework can be applied to any dynamic structural estimate. And in those papers, we usually impose the parametric model for the dynamic process, maybe AR1 process, maybe serially independent. Of course, in econometrics, we have some results about the identification and the estimation because we can treat the latent variable as a kind of unobserved heterogeneity. And some paper focuses on the identification of this unobserved heterogeneity. And other papers focuses on the identification of the finite dimensional parameters in the presence of infinite dimensional parameters. So in our case, it's a dynamic process of this latent variable. But it seems like in practice, researchers are using parametric model anyway. Maybe it's due to the computational convenience. Maybe it's because we believe the AR1 process is a good approximation to the data generation process. Maybe it's just because we don't believe assumptions for the non-parametric identification. So the contribution of this paper is we will have a reference dynamic process. So it's a reference conditional distribution of the future latent variable given the current latent variable. And we will define a perturbation set around this reference conditional distribution and to see if we allow for this perturbation, how does this change the counterfactual parameter? We will do this by computing its lower bound and its upper bound. And sensitivity analysis in econometrics is also not new. For example, for the dynamic discrete choice problem, we know we have three kinds of important assumptions. The first is the normalization of the utility function. Second is the marginal distribution of the utility shock. And the third is the utility shocks are serially independent. And the first two, their sensitivity analysis have been done. And this paper complements the existing literature by providing a framework for the specified dynamic process for the latent variable. And to do the framework, we will use the tools from the distributionally robust optimization. And I will talk about this later. Okay, I think we will spend most time on formulate the problem and how do we solve the problem. And we will try to interpret the results because for this specification, sensitivity analysis, everyone will ask about how do you interpret your result. And time permitting, I will also briefly talk about the very simple empirical application. So it's an infinite horizon dynamic event model. Okay. As we are working on a Markov decision process, we will have a reference conditional distribution of the future latent variable given the current latent variable. And we will perturb this conditional distribution in a flexible and non-parametric way. So we will define a perturbation set. So it's a non-parametric neighborhood around this reference conditional distribution. And we want to see if we allow for this perturbation, how does this affect a scalar counterfactual parameter, let's say price elasticity. And we will do this by solving the following constraint optimization problem. For example, for the lower bound, we are minimizing the price elasticity over the perturbed conditional distribution and over other model parameters. These other model parameters contain, for example, the utility parameter or the utility function and the value function. The value function here is a solution equation, and we call it structural constraint. And for the estimation part, we will use the moment condition. For example, it can be the model implied choice probabilities with the data. And the main challenge here is those three things. First, this perturbed non-parametric conditional distribution must have a station distribution. And this is the main contribution of this paper. And second is because this perturbed conditional distribution is non-parametric. Therefore, for this inner inf problem, it's an infinite dimensional optimization problem. And we don't know, for example, whether the worst case has a closed form expression or not. And due to this unknown property, it further complicates how to solve this Bellman equation. And also, because this latent variable is potentially serially correlated, and the value function here is also infinite dimensional because this latent variable is serially correlated, so it's informative about the future. And the value function is a function of this latent variable. And if this latent variable has continuous support, then the value function here is also infinite dimensional. So in this paper, we are trying to deal with the last two bullet points. Okay, it's a complex problem, but not that complex. For example, for this red part, if we only minimize the price elasticity over the perturbation set, this is called the distributionally robust optimization. We are minimizing over a distribution, the perturbed distribution. And in the DRO literature, we have many different methods to solve this problem. And the solution method mainly depends on how do we define this perturbation set. But in many cases, we will derive the due over this DRO primal problem because the most important thing is the due problem is usually computationally much easier to solve. And also, sometimes it can provide us with the closed form expression and the smoothness of this worst case distribution. And this closed form and the smoothness is helpful because we can use this closed form worst case distribution. We can plug it back into this Bellman equation so that we can update the value function during our optimization problem. So we still have two things to deal with it because we only know how to solve this minimizing the elasticity. But here we have a constraint optimization. Yes. Overestimate. Oh, so this is just to introduce what's the distribution robust optimization. What we want to do is this. Yeah. Oh, yes. This is a lower bound. For the upper bound, we can just replace this price elasticity by minus price elasticity to get the upper bound. Yeah. This is a lower bound. The framework can be also applied to obtain the upper bound. Okay. So as we have a constraint problem, we know how to solve the unconstrained problem. Then to convert this constraint problem to unconstrained problem, it's quite simple. We just write down its Lagrangian. This inner soup, the blue inner soup, the soup over Lagrangian multipliers for this moment condition and for this structural constraint. Or yeah. Yeah, right. So we write down the Lagrangian of the problem. And for this inner soup, it's the soup over Lagrangian multipliers for the moment condition and for the Bellman equation. And we will use the min-max theorem so that we can swap the order of this soup at the inf. And for this most inner inf problem, it is our distribution robust optimization problem. And we know how to solve this most inner inf problem. But the problem is how do we solve this outer min-max? The idea is quite simple. Just for this red part, we will derive its duality, or we will use the duality results from the DRO literature. And the good thing is that first, it's fast, and second, it will give us the worst case distribution. So we have a closed form. Then we can just use the worst case distribution obtained from this red part, and we plug this back to the Bellman equation, and we can update the Bellman equation during the optimization. So the overall implementation is quite simple. At each optimization step, what we do is we solve this inner inf problem using the tools from the DRO literature. We obtain the worst case distribution, and we plug the worst case distribution back to the Bellman equation. We update the value function. Then finally, we update those Lagrangian multipliers and, for example, the utility parameters. And how do we update those Lagrangian multipliers and the utility parameters? It depends on the specific problem we have. For example, in my empirical application, everything is non-smooth. So I use a Bayesian black box in math optimization problem for this, but it's still computationally tractable. So I think I don't have to recap this. For this infinite horizon single agent problem, we have three kinds of state variables. The first is the observable state variable X. For example, it can be the mile age in the bus engine replacement. And we assume for simplicity, it has discrete support. And we also have an exogenously evolving latent variable C. And this is our latent variable. For example, unobserved product characteristics may be technology short. And epsilon here is for simplicity. I assume it is RAD extreme value type 1. But the framework can also be applied to conduct sensitivity analysis with respect to this IID extreme value type 1 assumption. And here, our utility function is parameterized by theta. And theta here is finite dimensional. And beta is a discount factor, and J is our choice set. And to solve this dynamic programming problem, we will work on the Bellman equation for the conditional value function. So I don't think I have to explain this, but the conditional value function is at this period, we choose a discrete action J, it's not necessarily optimal, and we get this period utility. After that, we behave optimally, and we get this continuation value. And gamma here is the overall constant due to the IID extreme value type 1 assumptions. And we can see that to compute this continuation value, it depends on the conditional distribution. So it depends on this red part. The conditional distribution over the future C prime given the current D. And if this is misspecified, it will lead to the biased estimates of this continuation value, which bias is a solution to this Bellman equation, bias is the estimation, bias is the counterfactual predictions. Okay, so the main contribution in this paper is how do we deal with a stationarity condition? Because we have a reference dynamic process. It's characterized by the conditional distribution or the future C prime given the current C. And let's say, suppose it has a stationary distribution U0. And what we want to do is we want to perturb this conditional distribution in a non-parametric way. But this perturbed non-parametric conditional distribution also has a stationary distribution. So to impose stationarity, I start with its definition. We have a Markov chain. It is stationary if the current latent variable is drawn from the stationary distribution. The future latent variable is drawn from the conditional distribution or the future given the current. Then the marginal distribution of the future is the same as the stationary distribution. So it's defined by the second Boolean point. So motivated by this, I define the reference distribution to be the joint distribution of the current latent variable C and the future latent variable C prime. It's a product of the stationary distribution and the conditional distribution. Then stationarity is equivalent to that the marginal distribution of C, the marginal distribution of C prime, they are the same thing, and they are both the stationary distribution. So to impose this stationarity, we can borrow the notations from the optimal transport literature. This pi here is a set of joint distributions of C and C prime, whose marginal distribution of C is nu0, and the marginal distribution of C prime is also nu0. And this pi is borrowed from the optimal transport literature. And similarly, for any distribution F, any joint distribution F in this set pi, its conditional density has a stationary distribution U0. So to impose stationarity, what we do is we restrict the perturbed joint distribution. It should be in this set pi. And for the perturbations part, what we do is we define it to be the Kullback-Leibler divergence ball around this reference joint distribution. And delta here is the radius of this KEL ball, and it's a tuning parameter. And we will try to interpret the results in an intuitive way to choose this radius delta. So for this part, what we do is, as we fix its stationary distribution, so this perturbation set allows any dynamic process, we fix its stationary distribution, and it's around this reference dynamic process. But in the paper, if we want to further perturb this stationary distribution, and we also in the paper talk about how to do this. But in this talk, let's fix the stationary distribution for simplicity. Then as our perturbed distribution is a joint distribution, but our Bellman equation depends on the conditional distribution. So the Bellman equation here is a continual conditional moment restriction. And to convert to an unconditional moment restriction, we introduce this test function G. And we assume that this function class G is rich enough so that such that the solution V is a solution to a Bellman equation F and only if it solves this unconditional moment restriction. And given this, for notational simplicity, we can write our structural constraint for the Bellman equation as the last bullet point. So it depends on the finite dimensional utility parameter theta, infinite dimensional conditional value function V, and the infinite dimensional test function T. And we assume that V is the solution of the Bellman equation if and if it solves it. And for the estimation, we will consider moment condition. For example, on the left-hand side, it is a auto-implied moment. Maybe it the model implied choice probability. For example, P here is a conditional choice probability if we choose action A, given that the observable state is S and the unobservable state. And as you can see, and not in the data, integrate this C out using the perturbed. And the right-hand side is the data, and we will estimate this P0 from it. And let's say for the scalar counterfactual parameter, it's also a function of the finite dimensional theta, infinite dimensional V. And let's say we care about the average welfare, which is given by this. And what we want to do in this paper is we want to find the lower bound or the upper bound. And for example, the lower bound is given by the solution to the following strength optimization problem. We are minimizing the scalar counterfactual parameter subject to moment condition for estimation, subject to the Bellman equation, and over this perturbation set around the reference distribution F here. And delta here is a tuning parameter, so we can its lower bound is a function of the radius of the KL ball and the moments P0. And for this problem, we have some difficulties. We don't know process F is infinite dimensional, and it's the optimization parameter. We don't know whether the worst case distribution has a Poisson expression or not. We don't know what it is. And also, those three expectations, they are taken with respect to this perturbed unknown distribution F. If we have to do numerical integration, it's not necessarily the case that you know what's a good numerical integration method. And in this paper, we will derive the duality problem. And of course, this is a simple example. And if we want to further study maybe the cross-sectional dependence, for example, here we only have two marginal distribution constraints, and this is to study the serial correlation. If we also worry about the cross-sectional dependence, we can further partition this C and C prime into some subfactor study the cross-sectional dependence. And our framework also works for multi-marginal case. And of course, if we don't have this forward-looking, we only have the kind of discrete choice, the reduced form dynamic discrete choice form. Then the problem is even simpler. Don't have this. Bellman equation, we only have the moment condition for estimation. We only have a scalar counterfactual parameter. Okay. Recall that what we will do is we have a problem. We will write down its stuff. So the Lagrangian of this problem is the inner soup lambda here is a Lagrangian multiplier moment condition. But we assume we only have a finite moment condition. Therefore, this lambda is finite dimension. And we have a G. G here is the like multiplier function for the Bellman equation. So it's implicitly in the sign. And as we confirm, this problem is in the KL divergence ball around our reference point. So lambda K here, lambda KL here is the Lagrangian multiplier for the KL divergence constraint. And for given theta and V, utility parameter and the conditional value function, we will use the min-max theorem of this inner soup, inner blue soup, and this outer red ink, so that for this inner soup, for this inner ink problem, it's called the entropy transport problem. For the optimal transport problem, what we do is we don't have this entropy penalty. And the idea of optimal transport problem is we have distribution A, we have another distribution B, and we want to transport distribution A to distribution B with minimal transportation cost. And it turns out that it's equivalent to solving this, the first part for the problem. And this F with a fixed marginal distribution is called the transportation plan. And as we have the KL divergence penalty here, this is called the entropic or entropy regularized transport problem. And this entropy optimal transport problem has many good properties. For example, it has a unique worst case. But more importantly, based on this EOT duality, the worst case distribution has a closed form expression, and we also know it's smooth. And also we can think for algorithm. So this is a kind of the state-of-the-art algorithm to solve this entropy optimal transport problem and find the worst case. And this is computationally very fast, but of course almost negligible. And also in the dual problem, we will see that those expectations, they are taken with respect to the reference going distribution X area. So if we want to do numerical integration, we can use this X area to determine a good numerical integration method. 1 minute. Okay. Then this is a main theory of the paper. Part is we already talked about it before. So it's a min-max theory. It just means that we can swap the order of the soup and the mean. And the second part is the entropy optimal transport duality. So the role of the entropy optimal transport duality, it converts the optimization over distribution, optimization over function. So phi1 here is the test function for the marginal distribution condition for the currently variable. And phi2 is the test function for the marginal distribution condition for the future variable. And for this problem, we can see it's a concave optimization problem. And the single algorithm is an iterative algorithm to find the optimal phi1 star and the optimal phi2 star. And the closed-form expression is 5. And we can use this to solve the Bellman equation and to update the value function. So in the interest of time, I will briefly talk about how to do this in practice. Because this figure is from our dynamic demand model for new car. And the scalar parameter of interest in the industry-wide elasticity is at this period, 2023 December, if we increase the price by 1%, and what's the percentage change in the market share of making a purchase? And this black curve is a reference elasticity, and blue is the lower bound, orange is the upper bound. X-axis here is the KL divergence radius, and we will plot the lower and upper bound against this radius. And to try to interpret the results, the first is how do we choose the radius? So what we can do is we will have a reference dynamic process, AR1 process. We have some alternative parametric dynamic process, maybe serially independent normal distribution, maybe nonlinear AR1. And we can set the radius to be the KL divergence from this alternative parametric user reference dynamic process. And maybe it's most intuitive. And also, we can compute this, we can choose a very small radius. And this very small radius, the length of this rectangle. And this serves as a numerical derivative of the lower bound and the upper bound with respect to the radius evaluated at 0. So this is this derivative measure if we allow for very, very small relaxation. How does it affect the natural parameter? We have a very small one. We also have a very large one, for 10 to the power of 10. And we can treat this as a global sensitivity because in the paper I showed, if we choose a very large radius, it's more or less the same as removing the KL divergence, and we only have the circularity condition. So this lower bound and this upper bound, and the worst case lower bound, worst case upper bound. And in this figure, we can it deviates by at most like 15%. So if it's worst case lower, worst case upper bounds, they are already economically meaningful. Then we are fine with sensitivity.
All right. Thank you very much for the opportunity to present my work. So I'm actually an alumnus of this workshop back in 2019 before COVID. And this is the very paper that I wrote with the very that I learned from the instructors in this room. So I hope I can entertain you. Well, okay. This is a paper with Conan, who's at Michigan State in UT Indiana, and my name is Paul Ko. I'm an assistant professor at Yonsei University. To motivate this paper, I think it's fair to say that by now, empirical models of dynamic competition have become standard. So in order to talk about how to analyze dynamic competition with entry, exit, investment, and innovation, we know how to do that. But a standard assumption is to assume a particular information, is to make a particular incomplete information assumption when it comes to dynamic estimation of dynamic games. The idea is to assume that players observe their shocks, but not their rivals. And we do this because we want to try to bring the dynamic games model as close as possible to a single agent rush type of model. But we think that this is problematic, especially in dynamic games literature, because there's been less flexibility in terms of the types of informational assumptions that we've entertained in this literature compared to static settings. So the research question that we're trying to address in this paper is how strong are these informational assumptions? There are two ways to look at this question. First is robust estimation, that we want to be able to estimate dynamic games while being robust to informational assumptions. And the second is to think about sensitivity analysis. How strong is the standard incomplete informational assumption? So what we do in this paper is we develop an empirical framework or informationally robust analysis of dynamic discrete games. And by informationally robust, we mean that we're being informationally robust with respect to what players observe. So the idea is that we as econometrician, we don't really get to know what the player's information structure is. So we're going to be try to robust to that. And the specific type of notion of robustness is that we're going to allow players to observe more than what we assume as econometricians. So allowing for that arbitrary extra signal on the player's end, that's going to be the type of information robustness that we consider in this paper. So we make largely three contributions to the literature. The first contribution is that we develop a new solution concept that we dubbed Markov correlated equilibrium. This is going to be a solution concept that's a dynamic Markovian extension of what's called base correlated equilibrium. That's a solution concept in the static games literature developed by Bergman and Morse. And our contribution is to extend this solution concept to a class of empirical models that we use in empirical I/O. Second contribution is to develop a computationally tractable routine for estimation and inference. We're going to be largely relying on mathematical programming with equilibrium constraint, and we're going to try to argue that even in dynamic games, even if there are some non-convexities associated with dynamic environment, we can still handle that problem computationally. And the third contribution is going to be to consider a new empirical application, dynamic entry and exit game of Starbucks and Dunkin'. This is a new empirical application. Okay, so rather than presenting a general model, for this presentation, I'm going to be using on our empirical application, dynamic entry game of Starbucks and Dunkin'. So to motivate the empirical application, I want to show you this figure that shows you how the number of outlets for Starbucks and Dunkin' has increased in the US over the last 3 decades. So as you can see, the number of outlets operated by Starbucks and Dunkin' have increased pretty dramatically, indicating that there are some dynamics here. And when you look at the maps of Starbucks and Dunkin', Starbucks, starting from 1997, expanded pretty uniformly across the US, whereas Dunkin', their expansion focused more on the East Coast. So we want to be thinking about how to use dynamic games framework to analyze this game. Our idea is going to be to focus on the dynamics within each local market, and then think about the asymptotics with a large number of local markets. So here's the framework. Here's the two-player entry game for Starbucks and Dunkin'. We have local geographic market M, and within each local market geographic market M, we're going to have an infinite number of periods, which we denote by T. And each firm I in its period makes a binary decision. They can decide whether they want to be active or not active. And the action is denoted by AIMT. Firm I's flow payoff is going to be pretty standard. It's going to be a function of common market characteristics here. Firm I specific characteristics, because we know that having this excluded variable is important for identification. And also, it's also going to depend on whether each firm is an incumbent in the market or not, because this is going to determine whether they have to pay an entry cost if they're a new incumbent in the market. And also, we have this term that depends on opponent's action. This is the term that captures a competitive effect, or what makes this model game theoretic. That's going to be one of the key parameters that we're going to be interested in. And epsilon here is going to be the latent payoff shock that we don't observe as an econometrician. And our assumption for estimating this model is going to be to assume that firms play a Markov perfect equilibrium. So our goal as an econometrician is to estimate theta, the panel data of actions and market characteristics. So the thing that I haven't told you yet is how we make assumptions about this epsilon, what players observe about this epsilon, and that relates to the incomplete information assumption. The standard approach is to assume a particular form of incomplete information structure, in the sense that we assume that each firm I observes their epsilon, but not the opponent's epsilon. So I, as a Starbucks, I observe my epsilon fully, but I observe nothing about Dunkin's epsilon. So how the standard identification approach proceeds is that, given that incomplete information assumption, which we denote by SP, so this, you can think of this as a point in the space of information. Fix the information structure to be SP, and then we think about the data generating process of how, from model parameter, we get the distribution of actions and observable states. So it's the distribution that we observe as econometrician. So our job as an econometrician is to invert this mapping and then achieve identification. And under the standard regulatory assumption, we achieve point identification. But the problem here is that often there's little justification for assuming SP, this particular private information structure, SP beyond analytic convenience. And the results from the static literature has shown that misspecification bias associated with misspecifying the information structure of the game can be potentially large. So what we want to do in this paper is we want to think about relaxing information assumption. We want to think about allowing for a set of information structures rather than a point of information structure. So that's going to lead to a hard partial identification problem. To illustrate the logic of how the partial identification problem proceeds, here's our problem as an econometrician. So you give me a candidate parameter, and I want to tell whether this candidate parameter can explain my data. Because I'm allowing for a set of information structures, my question, given this candidate parameter, is to see whether I can find some information structure that can rationalize my data. So for a given set of candidate parameters, theta 1, theta 2, and theta 3, for each candidate parameter, I'm asking whether I can find some information structure S1 that can rationalize my data. This is the condition. You can think of this as the conditional choice probabilities. And I'm repeating that exercise and again for each candidate parameter. So again, for candidate parameter theta 2, I'm asking whether I can find some information structure that can help me rationalize my data. So if I repeat this and collect the accepted parameters, then I get an identified set. So that's my partially identified set. So what I want to argue here is that relaxing information assumption part, if we allow for a set of information. So to proceed with the argument, we want to be thinking about how to invert the data generating process once we allow for a set of information structures, right? So think about the data generating process, but rather than fixing the information structure at a specific information structure SP, think of allow for a set of information structure that we denote by bold S. And then if we apply the identification argument, you'll see that at the end of the day, we're just simply collecting Markov perfect equilibrium identified sets, taking the union set of that we're allowing. If that bold S, the set of information structure that we're considering is finite, then maybe things get simpler. But if we want to be really flexible with respect to the informational assumption, then computing the union of the identified set with respect to information structure, that becomes easily computationally intractable. Why? Because the set of information structures can be large and infinite dimensional. So what we propose in this paper is to say that rather than trying to take the union over a complicated set of information structures, let's treat the data as if it was generated by a Markov correlated equilibrium. So I haven't told you about what Markov correlated equilibrium is, but I want to first illustrate what we can do with this notion of Markov correlated equilibrium. Right. So rather than thinking about the Markov perfect equilibrium and the underlying data engineering process, let's just assume that our data was generated by a Markov correlated equilibrium. What we show in this paper is that if we do that and compute the corresponding identified set, then we get an identified set that is sharp and tractable. So it's sharp in the sense that if we compute the Markov correlated equilibrium identified set, that's going to be equal to the exact object that we want. So the right-hand side, what we have on the right-hand side, although I haven't really talked about what this bold S is, but this is going to be a complicated object. But what we can do is if we just Markov correlated equilibrium, we can get exactly that. So in that sense, using Markov correlated equilibrium gives us the sharp identified. We also show that Markov correlated equilibrium is tractable. Right-hand side is taking union over set of information structure. That's computationally hard problem. But if we just consider identification with Markov correlated equilibrium, that becomes a computation feature. So it's tractable in that sense. So the main message is that using Markov correlated equilibrium solves the information robustness problem when estimating dynamics. That's going to be the key result of this paper. Okay, so I want to show you what we can get if we apply this methodology. This is an example using the numerical example, the standard two-player entry-exit game example of Pessendorfer and Schmidt-Engler. So this is standard numerical example in this literature. So just specify the flow payoff in this way and make the standard assumption with respect to some the information structure. Turns out there are 3 types of equilibria, equilibrium 1, 2, and 3. And then depending on the equilibrium, that determines the entry, the different set of, there's different distribution of entry probabilities depending on the states of the game. So what we do is we, for each equilibrium, we observe the data and then we apply the Markov correlated equilibrium and try to get the Markov correlated by identified set. So if you do that with equilibrium 2, for example, then you're going to get some set, some partially identified sets. This is the true parameter, but the interpretation is that any point in this parameter, any point in this set it represents a parameter that can be supported by some information structure. So this is the informationally robust identity. We have a partial identified set, robust to informational structure. So quickly talking about what is Markov correlated equilibrium and how does it work, we need to review the notion of Bayes correlated equilibrium. So, okay, what is Bayes correlated equilibrium? Bayes correlated equilibrium is a solution concept that generalizes both Bayesian Nash equilibrium and correlated equilibrium in static games. To describe this, how people, the analogy that people use is to assume that there's an omniscient mediator, some mediator that observes the states or types of the players, and assume that this mediator privately recommends actions to players according to some joint distribution. Players receive that private action recommendation and think about whether they want to follow the recommendation or not. So this is just a description of a Bayes correlated equilibrium, but the question is like, is this really a good description of what's happening in the real world? The key point of the Bayes correlated equilibrium is that although this description seems weird, if we characterize the set of Bayes correlated equilibrium predictions, then that corresponds exactly to the set of Bayes Nash equilibrium predictions when we allow players to observe more than what we prescribe. So this is a tool for capturing information robust prediction. That's the result in the static games literature. So if you apply that to econometric analysis, then the message is in order to get the union of Bayes Nash equilibrium identified sets with allowing for players to observe more than what we prescribe. Just use Bayes correlated. That's really the key message here. So we try to bring that logic to dynamic game settings. So what we do is rely on the one-shot deviation principle. So here's the intuition. We know that one way of describing Markov perfect equilibrium is to call it a Bayes Nash equilibrium of an associated reduced form game. So it's a base Nash equilibrium of a associated reduced form one-shot game, in the sense that if you give me a strategy, stationary strategy profile, and I force players to play according to that strategy profile from the next period and onward, then we can think about the payoff associated with one-shot action. So that's how we can connect Markov perfect equilibrium to base Nash equilibrium of the reduced form one-shot game. We can do exactly the same for Markov correlated equilibrium. We can characterize Markov correlated equilibrium as a base correlated equilibrium of an associated one-shot game. So if we just show that these the induced reduced form one-shot game are equal as long as they induce the same distribution, then we can just leverage the result of Bergman-Morse theorem 1 and to say that Markov correlated equilibrium has exactly the same informationally robust informational robustness property. So really, again, the intuition is that by leveraging the one-shot deviation principle, we can report results from the static games literature to dynamic games. Okay, we show that computation is tractable, but let me skip this just to really illustrate what we can do. So going back to the empirical application of dynamic entry game between Starbucks and Dunkin', our question is, how sensitive can empirical conclusions be with respect to informational assumptions? So we try to obtain some data, define local markets using census tracts. Our market is something small, but we try to simplify the estimation problem as much as possible to really focus on the sensitivity analysis aspect. So here's the results. Here's the estimation results that we can get if we apply the standard tool, the Markov perfect equilibrium with private information structure. So this is the competitive effect parameter, which is of main interest. This says that if we estimate Starbucks and Dunkin's competitor using the standard Markov perfect equilibrium, standard incomplete information assumption, then we get positive spillover effects. That Starbucks enjoys the presence of Dunkin', and Dunkin' also enjoys the presence of Starbucks. That's probably us, although each firm's taking away each other's customer. Just having Starbucks next to me attracts more customers in the market. So eventually that turns out to be it's net positive. If we try to do sensitivity analysis with Markov correlated equilibrium, just focusing on these two parameters, then what we can see is that the signs of the competitive effects parameters become quite ambiguous. So be negative, it can be positive. So this conclusion that there's a positive spillover effect will be driven by informational assumptions. So that's one of the conclusions that we can get from applying our methodology. Using counterfactual experiments, we also consider the counterfactual experiment of reducing entry costs by 10%. We try to simulate the expected number of active firms in the market over time. So this is the yellow line is the dynamic of the number of active firms that we will get under standard solution concept with standard information assumption. But once we start relaxing the information assumption and try to think about the bounds that are robust to information assumptions, then it starts getting pretty large. This also illustrates that the conclusions that we will be deriving using the standard tool, they're largely driven by informational assumptions. We also try to decompose the effect. Is the largeness of the prediction, predict counterfactual bounds, is that coming from the largeness of the identified sets or because we have a set prediction? Well, we find that it's really the former, that it's because parameters are set identified, and because we have such a large partially identified set, that takes away, that's why we lose our ability to make sharp and precise predictions. Right. So to conclude, we propose an empirical framework for information robust estimation of dynamic games. We develop a theory of Markov correlated equilibrium, and we propose a computation tractable estimation and inference strategy based on Markov correlated equilibrium. One of the key lessons that we have is that standard information assumptions are far from innocuous. So I think this is really something to think about. And just to make quick remarks about future direction, possible future direction. One thing that we've learned is that space correlated equilibrium allows for too many things. So one way to see that is that if we assume complete information with base correlated equilibrium, it also it boils down to complete information correlated equilibrium, and that says that if we're using base correlated equilibrium, we're also allowing for the possibility for there to be a public random coordination difference. But as an econometrician, we want to think about whether that's a reasonable assumption, and maybe we want to rule that out. But if you rely on base correlated equilibrium or Markov correlated equilibrium, we can't rule that out. And it turns out that ruling out that type of possibility, that type of public coordination based on public signal device, it becomes a tricky problem. So there's definitely some room for improvement, and I think solving that could be a very interesting research. Thank you.